This is La Clock, an old Arduino project of mine I made for a maker class in college. The clock worked, but was always kind of fragile and falling apart, so I wanted to revisit it to fix up the wiring and clean up some of the code I wrote. The funny thing is that I still have no understanding of any fundamentals of electronics, of how things like voltage and current work. I made a video on a 555 timer tone generator circuit 12 years ago, and I didn't understand any of it then, and I still don't understand any of it now. For circuits, people always had this hydraulics analogy with water and pipes, but I have no intuition on how water behaves because I am not a plumber and have never messed with water pipes or pressure or pumps. So it's kind of scary how far someone or some machine learning model can get without understanding anything about what is being put together. But it's also a testament to how electronics can sometimes tolerate being used and abused outside their intended range. The main component of the clock is this big quad-digit 7-segment display, which I think looks quite good. We had to source our components from Adafruit to get reimbursed. On the store, they also had a backpack version of the display, meaning it comes with its own display driver chip, which would have made building this much easier. That display only uses 5 pins, as it uses I2C for communication, which is extremely efficient with pin count. I2C needs only one I/O pin for data and one for its clock signal. The clock signal also handles all the multiplexing for the digits. An advanced feature is that I2C with this backpack display can also handle addressing multiple displays chained together. I figured since there's not much else wired to the Arduino besides the display, I could get away with doing everything manually without a driver chip. So that's exactly what I tried. In the display, there are only 7 pins for the segments, so only one of the 4 digits is driven at a time by the 4 common pins, and it cycles through them rapidly. Then there's a 5th common pin for the other dots and 4 pins to control individual dots or the colon. If you count, there are 16 pins, and you will notice none of them are for power or ground. So I think I wired all of the current coming from the Arduino output pins themselves, which is not a good idea. Really, the current should come from switching on a transistor, which is how all LED displays are done. In my original wiring, I had the digit segments hooked up to the Arduino digital pins with no resistors, so I was lucky the display didn't burn out or damage the Arduino immediately. I had a bunch of resistors, but they were connected to the display dots, most of which I'm not using, and to the input buttons. I cannot explain that design decision other than I had no idea what I was doing, and I saw the display light up anyway. When I went back to redo this, I gave each segment its own resistor, so at least the LEDs got limited current and equal brightness. My thought was, with Ohm's law, if you assume the Arduino provides 5 volts and you give 20 milliamp current for the segments, then it works out to about 250 ohms. So I got 220 ohm resistors. As it turns out, the LEDs have a forward voltage drop of typically 4 volts, so around 1 volt is actually getting to the resistor. So if the segments get 20 milliamps, the resistance needed is only 50 ohms. But really, I can't drive segments at 20 milliamps because there are 7 segments, so 140 milliamps, but I'm trying to power all the segments with a common Arduino pin that supplies 40 milliamps at the absolute max and really shouldn't come close to that for safety. If I assume 1 volt with my 220 ohm resistors, I think each segment only gets 4.5 milliamps. As it turns out, my multimeter had a broken fuse, so it couldn't measure current, but I measured the voltage across the resistor and found out each segment was really only getting 2.5 milliamps. But it still shows up pretty bright, so I really don't know what's going on. If there's anything you take away from this video, do not do what I did here. Just get the driver chip and power everything properly from a power source. It'll be so much easier and less risk of damaging the Arduino and everything. The only electrical component actually in the breadboard are the resistors. Interestingly, if you have a bunch of parallel resistors, you can get a component called a resistor network that's all of them stuck together. There's versions with all the resistors isolated and also versions where they all share a common bus. I've never actually seen one in real life, at least in this large through-hole package. I probably didn't notice the really tiny SMD ones because they're so small. On the top, I have 3 arcade buttons of different arbitrary colors. They actually have built-in LEDs to light up, but I'm not using them. I did a really sloppy job soldering them with these blobs of solder. Some of these wires are the stranded kind, which I found harder to solder. The first button is the mode button. There are 3 modes for displaying the time, adjusting the time, and adjusting the alarm time. In display mode, I made the colon blink so you can see something is happening. The other 2 buttons increment the hour and a minute for adjusting the modes. A real clock should have an on-off switch for the alarm, but I didn't bother with more parts. The alarm beep comes from this little plastic speaker. I'm pretty sure it needs a resistor and a separate amplifier, but I just have it driven by the output pin. With a 220 ohm resistor and 20 milliamp current, I think it is only using 0.1 watts of power, while its max rating is 0.25 watts, so it's a bit quiet. The box enclosure is laser cut plywood with a laser cut acrylic front, held together with glue. There's holes for the Arduino USB and power jack, but I've never tested the power jack, so it might blow up or something. We were required to incorporate laser cutting and 3D printing somewhere in the project, so on the top we have this silly weather vane thing that does nothing I call le coq. There's really nothing in here that needs 3D printing. Maybe I could have had a proper stand for the Arduino, but really that was just the portholes being too high. Compared to the hardware, the software is so much easier it's not even funny. Arduino code is low-level C-like, but technically C++. The Arduino has a few hardware timers and one is already set up to provide milliseconds without having to mess with interrupts. My code loops, and every millisecond the code state switches to the next digit. There's also some simple state that holds the current mode, current time, and alarm time. It's not particularly clean, but it seems decent. There are only a few little details. One is I implement button debouncing in software. Sending too much serial output for debugging, even at a high baud rate, can actually slow down the code enough to interfere with the digit muxing, so I try to keep that at a minimum. One rookie mistake I ran into was storing time as an int instead of a long. On most computers, an int is 32-bit, but on some microcontroller platforms like this one, it is 16-bit, which is the minimum the C standard requires. I knew this going in, and I still messed it up, so the time overflowed way before it's supposed to. Finally, for fun, I tried making a messy cartoon breadboard diagram and schematic in fritzing. I'm showing you a screenshot because the program freezes every couple minutes on anything. Also, fritzing is open source, but the website charges for a downloadable binary. This is allowed under the definition of open source, but this is, in my view, suspicious and anti-user. I'm using a version that is somehow packaged in the Ubuntu repos, but still crashes all the time. I think the project has been dead for a while, and I would suggest using something that can produce a real schematic. I used KiCad for 5 minutes and I could already tell it was a much superior program in every way. Funnily enough, in this electronic book that I just bought, it shows you how you're supposed to wire up multiplexed LEDs. So the digits are supposed to be driven with these transistors. So do that instead. Anyway, I always end up saying more than I expect in making these videos. In conclusion, do not follow anything you see in this video. This will be my last hardware project because honestly, there is nothing I can make aside from trivial toys, and digital logic stuff is much more interesting for me anyway. Thanks for watching.